Hi, folks. It's time to look at 7.1 accumulation and net change. We have one more example to go through, and this has to do with the topic of work. So I could just read right through this. In everyday life, work means an activity that requires muscular or mental effort. In science, the term refers specifically to a force acting on a body and the body's subsequent displacement over a distance, right? When a body moves a distance d along a straight line as a result of the action of force of a constant magnitude F in the direction of motion, the work done by the force is W is equal to F times D. The equation W is equal to FD is the constant force formula, which I'll make reference to. It's kind of like when you push a desk. If you use the same amount of force and you push the desk over a certain number of meters, you're going to have an amount of work that's done because force is constant. Hooke's law for springs says that the force it takes to stretch or compress a spring, x units from its natural unstressed length, is a constant times x. In symbols, F is equal to kx, where k is measured in force units per unit length. It is a characteristic of the spring, or that is a characteristic of the spring called the force constant. Okay, so now I'm just going to go over what I have here so you can see that in number 1, or example 9, we look at a little bit of work being done. It takes a force 10 newtons to stretch a spring 2 meters beyond its natural length. How much work is done in stretching the spring 4 meters from its natural length? So if you have a spring, I'm just thinking of a spring that looks kind of like, let me see if I can draw it a little neater. If I have a spring that's attached here and it's kind of like looking like this, right? This distance would be its natural length. This is the natural length. And you can kind of see, like, what if we had a little place where we could attach this? So this is the natural length. I hope you can read that. It's really tiny, small, but natural length of the spring. That means it's at rest, right, before you pull it. And what you want to do is to be able to pull it in a direction where we're pulling. You can see that it takes a certain amount of force to pull on the spring and to hold it. So what we want to do is we want to know how much work is going to be done in stretching the spring 4 meters from its natural length. So if you picture that this is its natural length, we would start here at 0 for the natural length, natural length, and we would go 4 meters there this way. So we'd start at 0 as the spring is at rest, and we want to pull it 4 meters, okay? So now I wanted to do this number 1 first so you could see that if work is being done and the force is constant, all we really have to do is multiply the force. And remember, the force is in newtons, and we'll talk a little bit about that tomorrow. But with force being in newtons, all we have to do is take those 10 newtons, kilogram meter per second squared, times the meters, 2 meters, and we end up with 20 newton meters for our work that's being done. Okay, and so we don't want to do that. I almost want to get out the heat-seeking red flare here and go, no, we don't want to do that here because the force is a variable force here. So, and in this formula that you have up here, when you're dealing with Hooke's law for springs, the force is governed by this formula, Kx. F is equal to Kx, where K depends on the material that the spring is made out of. So it's a given in each problem. So what we're going to do first, it says that work, it takes 10 newtons to stretch a spring 2 meters. So that would be half as much to 2. So work will vary because force varies, but K is a constant. K is a constant having to do with the material of the spring. So we take F is equal to Kx, and we have 10 newtons is what our force is, and it's 2 meters, and we solve for K. So we get K is equal to 5. So that gives us our equation, our K value for the equation for F is equal to Kx. So it's 5x, just a linear equation, right? So I put in a step 2.5 here where now what we want to do is we want to add up all of the f of x dx's. Now in this f of x dx, every time we move a little bit further, every little dx or small change in x along from 0 to 4 is going to have a force that can be considered constant. But these are infinitesimal delta x's. So, what we have to do is use calculus with that. So we want to take the limit as the number of subintervals, those number of sections, goes to infinity. And the number goes to infinity, but the size then goes to infinitesimal. So that's our step 2.5. And then 3, so all we have to do is really add up the infinitesimal delta x's on the interval. And so we get the work is equal to the integral from a to b of f of x dx, which is 5x for f of x. And then we're going from 0, the natural length, we're going to stretch it 4 meters. dx is in meters. 5x has units of newtons, okay? So then what we do is go from 0 to 4, 5x dx. We integrate. We get 5x squared over 2, evaluate from 0 to 4, and we end up with 40 Newton meters. Now, I'll let you look up the units for Newton meters. You might feel rather rich after we did this problem. And that's all I have for you tonight. That'll finish up 7.1. And what I decided to do is go a little bit rogue, and I think we're going to have a 7.1 day 2 on Wednesday. And then we're going to push 7.2, and that would be area between for Thursday, and let's hope we're going to be here on Friday. So you guys have a good night, and I will see you when I see you back here at 417 400 Hallway, Sauk Valley High School. I will see you then. Take care, kids.